G'day fellow solar power enthusiasts. My name's Chris and I'm the developer at Empowered Apps. This is a video to show you the fastest way to design your own solar power systems using the SolarPower App available on the iOS App Store. If you've already downloaded the app, thank you, and if you haven't already, click the link in the description and check it out. Either way, we look forward to helping you design your own solar power systems. SolarPower App arose out of our experience living off-grid and needing to design, build and maintain our own solar power system. To wrap my head around solar power, I initially had to spend hundreds of hours researching, often to answer simple questions, plus many hours of trial and error to finally build a system that was appropriate, low maintenance and safe. Yet I could see that if all this information was pulled together into one place and given a logical flow, that people would be able to design their own solar power systems in an hour or two, if not minutes, while saving thousands of dollars sourcing parts at the best prices. Thus SolarPower App was born. So the purpose of this video is to walk you through designing a solar power system for an off-grid cabin. Additionally, I may add links in the description to another 2 common solar power system builds to demonstrate how each project is specified using the app. Let me know in the comments if that would be of help to you. The other types I think would be helpful are a grid-connected home as you would get in the suburbs, and an off-grid motorhome. Okay, let's dive into the app and design an off-grid cabin power system. On entering the app, you are shown the My Projects screen. This is a management screen the app uses to store all of your solar power projects. First of all, a heads up. If you are disconnected from the internet, you will get this alert. To design projects, you must be connected to the internet. This is because the nearest weather station statistics and complex modelling data needs to be retrieved from the internet to work out how much energy your solar power system will generate. If you do not have an internet connection, you can still view your existing projects, but your ability to modify them is limited. On your first use of the app, it is important to fully review the README file by tapping the name at the bottom of the screen. The README file contains important considerations that you should take into account when designing your solar power systems. Returning to the My Project screen by clicking Done. Now throughout the app, you can click on the question mark icon to access a help guide for that screen. The help guide will list all functions on that screen, what each value means, and how to find any input data the app may require from you. We've also included a Contact Us button at the bottom you can use to send an email with any questions, feedback or issues. I'd also love to see any builds you complete using the app, and let me know if we can feature them on Instagram to inspire others. Now above any list throughout the app you will see an Edit button. Tapping this enables us to delete any items that we no longer need. Okay, so the only thing left to do is add our off-grid cabin project by clicking on the Add button in the top right corner. So let's type cabin as the project name. Next, the project asks what cable loss value we want to use. All wire cabling causes voltage loss as electricity travels along them, and to minimize this you have to use thicker cables. 2% loss is the default most systems use as a trade-off between wire cable thickness, which affects costs, and system efficiency. So in our projects we'll leave this default value. We can also choose what units we want to specify our cable lengths in. As I'm an Aussie, I'll select meters. Next we need to specify whether our project is connected to the grid, battery or both. We'll select our cabin as connected to batteries by tapping the slide button. And now we can click Done to return to our project list. Okay, now we can see our cabin project in our list and it tells us it is off-grid, meaning a battery connected only project. An eye or information icon has also appeared to the right and we can click on this to get a basic diagram of what components our system will require. The diagram uses color coding to show any changes in voltage and changes from DC to AC electricity. If you are building a system that will only use DC electricity, for example a 12 or 24 volt system, then the AC components won't be necessary. If you plan on using mains electricity however, then you will need the AC inverter to convert the DC electricity your solar power system produces to the AC electricity your appliances will need. At the bottom of this screen is a selector that allows you to choose between different options like the base setup, meaning separate components for each function, or things like inverter charger, or IPS, meaning integrated power system. These last two are where components are integrated, thereby reducing the number of items in the system. More and more integration options are becoming available, and whether you decide to use separate components or more integrated ones is a decision that is influenced by your build, your budget, and your preference. We'll talk more about this later. You can always return to this diagram to visualize the layout of the system you are designing. For now, we can close this screen by clicking Done. So let's move on with our build by tapping on the row titled Cabin. This brings us to the main index of our build and shows us what sections are accessible depending on where we are at in our build or whether we are connected to the internet or not. A check mark on the right hand side of a row tells us that the app has all the data it needs for that section. We can verify this by tapping on the Project Details row. Here we can see the information we entered when we created our project. Project name, cable loss and measurement units are editable, but the system connections are not. If you need to create different system connections, you will need to create a new project. Let's return to the main section index by tapping the back arrow. So the next thing to do is specify the location of our project by tapping the second row. This brings us to a map view with a search bar at the top and a button bar at the bottom. We also have a selector button at the bottom of the map that allows us to choose between different map types. Often the hybrid type is most useful, as you can find the exact location where your solar panels will go. If you're installing the solar power system at your current location, you can tap the first button on the bottom and enable location services so the app can drop a pin and zoom to your current location. Otherwise you can use the search bar to find an address. You can also tap the screen to drop a pin, or drag the existing pin to the exact location. You can tap the Add button to drop a pin in the center of the map. You can tap the Undo button if available to revert the pin to the last saved location on the map if there is one. And you can tap the Reload button to remove your pin from the map. Once we're happy with the location of our project, we can return to the project sections by tapping the back arrow. You may see a downloading data alert as the app retrieves climate and modelling data from the internet for the project location. Now it's time to specify our electricity use, so we tap on the third row. The purpose of this section is to capture how much electricity needs to be supplied by our solar power system. It is able to capture two types of electricity, mains voltage AC and low voltage DC. If your project needs both types of electricity, then the app can accommodate that. If you know your exact power requirements, say because you have existing power bills or you have been monitoring with an electricity meter, then you can enter those amounts in the daily use rows here and here. When designing an off-grid solar power system, it is important to work out what your maximum daily use is and use that figure here. Let's say that I have a year's worth of power bills and I can see that I use 8 kilowatt hours a day of electricity in winter, but that rises to 14 kilowatt hours a day during summer because my fridge has to work harder and I run a few ceiling fans and sometimes an air conditioner. Then I would enter 14 kilowatt hours here. Now I need to specify what the highest amount of power we'll use at any one time. Unless you have an electric stove or oven, often the highest power is things like boiling an electric kettle that will use 2 kilowatts. So if you add that 2 kilowatts onto the items that are constantly running, like a fridge, fans, computers, lights, etc., then you might want to specify up to 3 kilowatts. Now we need to specify what our mains power supply is, therefore what voltage our appliances need, which can change from country to country. If you're not certain, you can look it up on Wikipedia. Here in Australia, the official mains voltage is 230 volts AC. Okay, I'm also wanting to run some lights and an extraction fan in my battery shed directly from the batteries, but because I'm not certain how much these appliances will use, I'm going to get the usage calculator to work it out for me. So here in the usage calculator, I can build a list of appliances that I need to run. Let's add those DC lights by tapping on the Add button. I'll enter lights. I need 2 of them. The advert online tells me that they use 10 watts each, and the longest they will need to run is 2 hours if I have to do maintenance on the power system. Lastly, I select that they are low voltage DC and tap Done to return to the list. Okay, let's repeat that process with our extraction fan. Which uses 40 watts and will need to run up to 14 hours a day in summer. Again, I'll tap low voltage and then Done. Okay, so now we can see both items on our list with their details underneath. You can also tap on each of these items if you need to edit them, or you can tap on Edit to delete any you no longer require. Let's return to the electricity use screen by tapping the back arrow. Now we can see a total has been added to the DC low voltage daily use. Our peak wattage is going to be the 40 watt fan plus the 2 10 watt lights, so we enter 60 watts, which is 0.06 kilowatts. And these are 12 volt appliances. Total usage of 14.6 kilowatt hours a day for our cabin is now calculated. We can now tap the back arrow to return to our section index. Now the app wants to design our battery bank, so we tap on that row. Our battery bank requirements want to know how many days of storage we'd like. for when we don't receive any or minimal solar charge, in essence during heavily overcast days. The usual for off-grid systems is 3 days, but you may want more or less depending on your climate or how accessible and cost efficient other sources of charge for your batteries are. For example, a motorhome may only need 1 or 2 days storage because its batteries can also be charged while the vehicle is moving, or it can be connected to mains power easily. For this project we'll leave the default at 3 days, and that means we need a total of 47.47 kilowatt hours of usable storage. The red highlighting means we haven't met this requirement yet, so we tap on the Add button to add our battery bank. First thing we need to do here is specify the batteries we will be using in our battery bank, so we tap on that row. If you don't know what battery you want to use, then I'd recommend doing 2 things. Have a read online of the main battery technologies for off-grid power systems, and what the advantages, disadvantages and preferred applications are. And then use the links to Amazon and eBay at the top of the screen to research the different models and costs of batteries appropriate for your build. For example, with our off-grid cabin, the weight and size of the batteries are not an issue, so we can go with heavier, larger and therefore lower cost options, like the most common battery technology, flooded lead-acid cells. In a motorhome where space and weight are at a premium, the higher cost of lithium batteries may be more justifiable. So for our cabin, I'm just going to click on the default button to give us a generic lead-acid battery to use in our system. So now we can see the table has been populated with flooded lead-acid cells producing 2 volts each, which is common in the larger deep cycle lead-acid batteries. Deep cycle meaning these batteries can be used to a greater discharge depth and cycled many more times than say a standard car battery. As you can see, flooded lead-acid batteries are reasonably efficient at 90%, but can only be discharged to a depth of about 50% of their capacity if we want to maximize the number of discharge-recharge cycles and therefore the life of the batteries. Depending on the cells you end up going with, you can adjust these numbers to match the manufacturer data. Okay, let's tap the back arrow and build our bank with these battery cells. Now the app has automatically calculated the possible size and layout of our battery bank needed to meet our requirements using these batteries. First figure we need to check is the capacity in amp hours, which is a measure of battery capacity calculated by looking at how many amps over time, measured in hours, can be discharged from the battery. In our case it's unlikely we'll find a 1979 amp hour battery, which would also be massive and difficult to move, so let's change that to 1000 amp hours. The app has also worked out what the best possible layout of our battery bank would be and has specified 1 string of 24 batteries at 2 volts each, to give us a total bank voltage of 48 volts. Because we lowered the battery size to 1000 amp hours, this only meets half of our needs now. So we now need to double the number of batteries. We do this by specifying 2 strings of batteries, which means 2 rows of 24 2-volt batteries. This now meets the needs of our system, leading to the green highlight, and shows the actual bank size is 96 kilowatt hours because we only want to discharge the batteries to 50% as the norm. If you want to learn more about battery bank layouts, you can tap on the help button at the top of the screen. One thing to mention is that this is a very large battery bank in terms of both electrical storage and physical size. This is why it is always best to reduce your electrical needs through efficient building design, efficient appliances and mindful practices. So now we have our battery bank, let's tap on Done. So again we have a green highlight showing us our energy storage requirements have been met, and some summary information about our battery bank is presented. From here you can tap on your battery bank if you need to change anything, or you can click on the Edit button if you need to delete a battery bank. Let's return to the section Index with the back arrow. Specifying our batteries has now unlocked our solar array section, so let's build our arrays now. So the Solar Array Manager screen has a similar table list at the bottom to the Battery Bank Manager, and this same manager format is used in all the component sections. At the top of this screen is an option to specify site day length. A small number of users have reported issues with this section, which is related to the online server it accesses. So if site day length is absent from this screen, or you continually get a re-download alert when you try to use it, it means your app has been unable to reach the day length server. But for us, it is working, so let's tap on it. The purpose of this screen is to fine-tune the day length of our installation site. If there are trees, landforms or buildings that cause shading of the panels, then that can be accounted for here. Important to note that you don't need to account for any shading that occurs from your solar panel orientation, east, west and their tilt. That is all taken care of by the scientific modelling. So for our cabin, which is in the southern hemisphere, let's say the winter sun angle creates shading from trees, meaning sunlight doesn't hit our panels until 9 AM. So we can adjust that value. It is also off our panels by 5 PM for the same reason. Because of the overhead passage of the sun, our summer day length can remain unchanged, so we can now exit that screen. Okay, so returning to the Solar Array Manager, we can see that 18.68 kilowatt hours of electricity per day is required from our solar array. Let's tap on Add to see what size array we are going to need to meet that. So first the app wants to know what months to include in its assessment. The purpose of this function is to exclude certain months from your solar array's calculations if you need. For example, if the cabin is not occupied during winter months, or if it's at extreme latitudes and the sunlight is so low, you need to use other sources of energy, like a generator. Underneath each month is the average daily solar irradiation per kilowatt of panels that can be harvested at the project location. This may help you decide if you need to exclude any months because the rate of solar harvest is not feasible. Because our project is in the tropics, we don't need to remove any months from our calculation, so we can tap the back button. Now we need to specify the way our solar panels will be mounted. First we select the mounting type. For most projects the panels will be mounted on a fixed angle, either on the roof or on a frame mounted on the ground. Also for our project we could use a ground mounted frame that can be tilted manually, and we could adjust every 3 months to maximize our solar harvest. Selecting this option automatically calculates the best angles and what months we need to adjust the tilt. However, we will use our cabin roof, so we select the roof mounted open rack. We then need to specify the tilt angle, or we can use the button underneath to choose the best angle for our needs, like a yearly average, which at our location is 16 degrees. However, the panels will be attached to the roof, which has a slope of 20 degrees, so we have to select that. Finally, we need to set the azimuth, that is the direction the panels will be facing. Our cabin roof faces east and west, so we will build 2 arrays. We will have half our panels facing east and the other half facing west. So let's build the east facing array first. Now we can return to the previous screen, and the app will retrieve data from the internet using our mounting specifications, location, and run calculations using the location climate data. Our next step is to specify the solar panels we will use. Here, like in the battery section, we need to do some research and find the best panels for our needs and budget. Again, browsing the reviews on Amazon may be a good place to start. Once you have found the panel that best meets your needs, download its specification sheet from the manufacturer and enter the data in the text fields below. For our cabin, I'm just going to tap the default button to get a generic panel to use in our system. From here we can return to the previous screen. Next we need to connect the array to the battery bank. And because we only have one bank, it's straightforward. We'll call this array east. It's best to minimize the length of any cabling wherever you can, so we will place our panels in 2 rows and our batteries in a dedicated storeroom at the end of the cabin. This will keep the length of the cable we need to 6 meters. So the app tells us we need a 5.14 kilowatt array, which means 20 of our panels. So our first array will use half of those. Now we need to specify how many panels will be connected in series, which increases the array voltage, versus in parallel strings, which increases the array amperage. Basically, this is a balancing act of keeping voltages safe. Some recommend a maximum of 120 volts DC if self-installing, and below the max voltage your charge controller can accept, a component that we will talk about more in the next section. Some countries also have legal requirements around what voltages self-installers are permitted to use. You also want to minimize the amps your array outputs, as bigger amps need bigger cables, which can add to the system cost, weight, and the difficulty of routing cables. So we'll choose 5 panels per series, which then means 2 strings to make up the 10 panels. As you can see, the app has calculated the array output as 154.5 volts and 17.46 amps. We have now finished our first array and can tap Done. As we can see, the daily solar total is not sufficient for our needs yet, so we need to build our west-facing array by tapping Add. Okay, we now repeat the same process as with the east-facing array. Clicking Done, we can see our solar arrays now meet our power requirements, and we can return to our list of sections. Now our charge controller and inverter sections are visible, so let's build those now. A charge controller is the device that goes in between our solar panels and our battery bank in an off-grid system. Its purpose is to convert the volts coming in from the panels, which are highly variable, and in our case up to 154 volts, to the nominal voltage of our battery bank, which is 48. It also controls the voltage and amperage to optimize the output of our solar arrays, and can smart charge our battery bank to optimize the charge speed and the health and storage capacity of our batteries. As we can see, we have 5.4 kilowatt of solar arrays that we need to connect, and also 70 watts of DC load to power those 2 lights and fan in the battery shed. A charge controller manager also shows that we have 2 arrays waiting to be connected as well as our DC load. So let's add our first charge controller now. The first thing we need to do is to connect our battery bank and then connect it to our arrays. Most charge controllers only accept 1 input, though there may be models out there that accept 2. For now we'll go with 1 input, and because the arrays face different orientations, I'll need 2 charge controllers, as combining the east and west arrays on the same circuit will cause the panels receiving less sunlight to drag the output of both arrays down. There are devices that you can fix to the back of each solar panel called optimizers that negate this effect by stabilizing all the solar panel voltages. Basically, they are mini charge controllers / regulators that deliver a constant voltage from each panel and vary the amperage instead, which stops an underperforming panel, whether by shade or fault, from dragging the whole array output down. If your panels will receive a lot of patchy shading, or you want to be able to monitor each panel's performance to detect faults or underperformance, you may want to invest in optimizers to maximize your solar output. For this building, we will not be using optimizers, so I'll go ahead and connect the east-facing array. We can now return to the previous screen. This has revealed a lot of new fields and also some important information we need to find a suitable charge controller. Again, at this point, you will likely need to do some research to find a charge controller that meets your requirements, and links to Amazon and eBay have been provided for this purpose. In our build, we need to find a charge controller that can accept at least 192 volts input from the solar array, and can output at least 56.2 amps to the battery bank. We also need to cater for our DC load, as some charge controllers can manage the DC load as well. I've already done my research and settled on a Victron Energy Smart Solar 250 volt by 60 amp charge controller, so I'll enter its specifications now. Again, it's best to keep your cable runs as short as possible, so I'll put in 1.5 meters to account for the fused circuit breaker that will be needed between the charge controller and battery bank. Our charge controller does not come with an integrated load controller, and given our DC load is 12 volts and our bank is 48 volts, I'll just connect it directly to the battery bank with a fuse and a 48 to 12 volt step-down converter. To satisfy our load requirements, I'll just add that info in here. We can now tap Done. Our connection manager has been updated and we can see one of the arrays and our load are connected. Let's specify the same controller again, this time for the west facing array. So we just complete the specification as per the previous controller. And now we can tap Done. Okay, now our connection manager is happy with both arrays and the load connected. So let's return to our section list. Next up is our inverter. Many of you will know that an inverter is a device that can convert direct current or DC electricity into alternating current or AC electricity, or vice versa. Because we still want to use appliances that run on mains AC electricity, we will need an inverter. So our inverter section shows us that we need a 3 kilowatt inverter to meet our power needs. Let's add that inverter now. The first thing we need to do is connect our inverter to the battery bank. This now gives us the parameters we need to find a suitable inverter. In our build, it will be an inverter that takes a 48 volt DC input and outputs at least 3 kilowatts of 230 volt AC electricity. Again, I've done my research and decided on a Victron Multiplus 2. It also comes integrated with a battery charger. Unfortunately, the most suitable size is the 5000 VA model, which can output 4000 watts. So we have a bit of extra headroom if we decide to expand the system later, but this does make it expensive. Again, we'll keep our cable run as short as possible while including the extra length needed to mount the fused circuit breaker. At the bottom of the screen, we also have the ability to specify if it is integrated with our charge controller. This is because there are all-in-one units for solar power systems available these days, called Integrated Power Systems or IPS. Whether you use an all-in-one or separate components in your power system is up to your project requirements and your personal preferences. We can now see that our inverter requirements have been met. Our last piece of equipment to specify is our battery charger. SolarPower App will let you build your system without a battery charger, but a battery charger and a generator are pretty critical in an off-grid system to give you backup options in the event of more than 3 completely overcast days where you have no solar input and you need to charge the batteries by generator. It's also useful anytime you have a fault in your system or need to do some maintenance on the system. Our battery charger screen shows us that the optimal charger output would be 4.9 kilowatts, though this is just a guide and it isn't mandatory that we meet this. The system will accept a battery charger of any size. Now our battery charger was integrated into our inverter, so let's put those details in now. At the bottom of the Add Battery Charger screen, we need to select that it is integrated with our inverter, and we can then select our inverter that we created just before. Alright, we can click Done and now see that our battery charger has been added. We can now return to our Sections screen. We've now completed our first solar system build, so let's go ahead and view it in our specifications. Okay, we are presented with a rolled up list of different sections. You will recognize the sections for our components, but there are also sections for a project summary, for our cabling, and also if our project has triggered any alerts, we will have a section for that. So clicking on Show for our project alerts, we see that we have 2 alerts. One for the mismatch that we discussed earlier about our 48 volt battery bank and our 12 volt lights and fans in our battery shed. In our case, we will use option 1 and use a step down converter to turn the 48 volt into 12 volt for our lights and fan. A second warning is that we have exceeded ultra low voltage DC of 120 volts in the electricity coming from our solar array. If we are competent in working with such voltages and it is legal in our country to do so, we may choose to connect it ourselves. But in our case it is illegal in Australia for do-it-yourself installers to have voltages above 120 volts in their system. So I will ask an electrician to comment on the final design of the cabling from the panels to the charge controller and have them hook up that part of the system, likely when they hook up the 230 volt AC circuit. Now on to the project summary. This section gives us an overall view of our project and system specs. It also makes a good place to check for any obvious errors with our project or system, and we can go back to the sections and fix them up. In our case, everything looks okay, and we can scroll to the graph at the bottom. This graph shows the average daily output from our system during each month of the year. As we can see, our lowest solar energy is 19.3 kilowatt hours in June, which is winter solstice for the southern hemisphere. But for many spring and summer months, our system will generate far more than the 14.6 kilowatt hours we will use, so it would make sense to use as much of this extra power during the day, things like pumping water into tanks, or ceiling fans, or even that air conditioner in our cabin. So we can cycle through all the other sections to check our build and make sure we haven't made any errors. For our build, everything looks good, so we just need to see what cabling our project has specified. Okay, so each connection that requires wiring is shown here. We can see which components are being connected at the top, followed by the specifications of that connection. The wiring is specified as both cross-section in millimeters squared and in American or Brown and Sharp wire gauge. So we can see our east array needs at least an 8 gauge wire to keep our cable loss under 2% and to safely carry our amps without the wire getting too warm. Lastly, the app tells us what size DC fuse or circuit breaker the connection will need. Generally, circuit breakers and high current fuse enclosures are used in solar power systems, as these allow for system components to be quickly isolated or shut down in the event of a fault or hazard. So from here we are ready to start pricing and ordering the major components for our solar power system. There are also a lot of other components, consumables and tools that you may need to build your system. So I've included a list of additional components here with direct eBay and Amazon links. That brings us to the end of this tutorial. Thanks for watching, and I hope you feel empowered to start designing and building your own solar power systems. Please let me know about your experiences with the SolarPower app or any questions you may have. And if you use SolarPower app to build your system, we'd love to see it and feature it on our Instagram page. Thanks everyone, and all the best with your solar power system build.